Hey, welcome back to Shop Talk. Episode number 6, I guess, isn't it? We're going to be talking about expansion tanks, and I've got some slides. We're going to talk about sizing. We're going to talk about everything about expansion tanks, and then I've got a little demo running behind me that we pre-filmed the video. But if I have to, I can go back to this. If there's questions about something specific, I can go and we can play around with it. So a couple housekeeping slides on the front end here, and we'll get we'll get right into it. Yeah, thanks everybody for showing up tonight. Yeah, these are just things as far as the format to go to webinar people if you have trouble breaking down or something. And this maybe you can use in the future on other go to meeting or go to webinars. That's just their tech support line, and also the where you can find the past episodes that we've archived either on our website or on Mechanical Hub. Also has them archived there. So if you want to look at one of the previous presentations we did or review one of them or whatever, that's where you can find them in both those spots. And again, thanks to we got a couple people from Mechanical Hub, I think, online today helping us for with this, and thanks for promoting it, and kind of their idea really that we started this whole thing. So thanks to the whole team over there at Mechanical Hub. And yeah, there's the number of all the fundraisers that we've done since we started. We've raised over $2,300. So that's a big thanks to all you folks out there. And those are some of the charities we started with: the Samaritan's Purse and American Red Cross, Meals on Wheels, World Central Kitchen, the dog shelter last week, and then today I think Mary's got one teed up that we're going to do the Ronald McDonald House. In fact, there's the team, our Caleffi team, went to Ronald McDonald House up in Milwaukee there, and fed 80 people, I think Mary said. They put together a chicken and I think a ham. They went up there and cooked it and did the salads and everything, and served 80 people at the Ronald McDonald House up in Milwaukee. And they're always looking for people to do that. So if you have time or you're inclined, or you've got you want to take your company down to do that, they're always looking for people to help them out, either donation, of course, or to go down and put some time in. So yeah, please do that for us. All right, and then what we're going to do, oh, it's even animated in there. Starting in June, we're going to have Siggy's going to come and do, I think it's a 4-week presentation. He's going to go through, he just built a house for his daughter right next door to his house, and put in some really unique systems there. Obviously a low energy house, and he put in some heat pumps, air to water, and also air to water and a water to water system. So he's going to go through the design of that and how he put it all together, probably some live pictures of how that's working. I know it's gone through some cold times since it's been put in, so he's going to give us some real live data on how that system's performing. I think it actually exceeded his expectations as far as the temperatures he's been able to run with that, and keep the house warm, keep it heated. So that'll be interesting. And it's I think it's a technology that we all want to start keying into. If you're in any of these areas where they're trying to go fossil free, all electric, what are your options? Well, these heat pumps are looking like that might be the way that the hydronics can still play in it, because it's going to involve radiant heat, buffer tanks, and some of the stuff that we play in that we are familiar with, so we don't lose all that that business to like mini splits or something like that. So this will be a pretty timely series that we do with Siggy, and he always comes prepared, as you know. It's always his A game. So some of the in fact, a lot of the slides I'm going to be showing today come up of our hydronics issues. Hopefully everybody's receiving these. It's a technical journal, comes out twice a year. It's free. If you want these mailed to you, just go to our website there, caleffi.com, and you can sign up for these. Issue number 27's getting ready to release. Yeah, these are great. You can get back issues. Let us know if you want some of the back issues. I like the hard copies so I can make notes in them and stuff like that. They're also on our website as a PDF file, so if you want to go and look up some of these schematics or something that I'm using tonight, you can just go back. I try and leave the figure number in them so you can find them in the issues and that, but they're all there for you to enjoy. All right. So expansion tanks. Let's see. I got to do I think I got a slide in it here for our trivia question as we get going here. And we also got to do some polls. We've got a couple new things tonight that we're going to throw in here. So let's get going. But that's what I want to talk about mainly, is the expansion tank is the theme tonight. I'm going to talk about the different types of tanks that you see out there, how they work, some of the issues when you go to replace an old style tank with a new style tank, some of the things that you have to be aware of, sizing them, how to go about that. Oh, there's the trivia question. So it's going to be another lyrics, I need to know the name of the song and the artist. I'm gonna put the year in there too. Maybe we should do a 3-fer on this one, Mary. I need to know the artist, the year, and the name of the song. And the lyric goes, and probably everybody's gonna know this one. Sometimes you're the windshield, sometimes you're the bug. That's the lyric. Sometimes you're the windshield, sometimes you're the bug. Who is the artist, the name of the song, and approximately the year that was popular. So see what you have there. We've got the T-shirt that you see there on the screen. Is going to be the gift. All right. So of all the places I think that I've learned the most about expansion tanks and pumping away and the point of no pressure change, I would say these are probably on the top of my list. Dan Holohan wrote that pumping away. I think actually Dan's, I don't know if he's on here tonight, is going to be doing a webinar himself on pumping away here within a week or so. If you go to heatinghelp.com, you can find out more information about that. You'll learn from the guy that wrote the book on it, so to speak, pumping away. But it's kind of interesting on these two that I've got up on the screen. There's kind of the extremes as far as the presentation. Dan does it kind of with cartoons and makes it fun and interesting, and takes it down to a really understandable level for somebody that probably didn't even know anything about hydronics. By the time you go from cover to cover on pumping away, you'll have a pretty good understanding about what that means, pumping away, and be able to understand it and explain it. On the other side there, the Amtrol engineering handbook, a lot of math in there, a lot of numbers, a lot of theory, a lot of small print. I mean, it was written probably by engineers, so a completely different style in how they present the information, but it's the same information. But interesting about that Amtrol engineering handbook, I got the revision here. I think they've revised it at least 4 times over the years, and they finally put it on their website as a free download. So there's the web address. If you just go to Amtrol, you can also scroll through there and find it. But a lot of really good information there about all types of different expansion tanks. I mean, Amtrol claims to be the original designer of the diaphragm type of expansion tank. So obviously they talk a lot about that. But things I didn't know about, like how do you size the line going to expansion tank? There's actually formulas for that. Really don't come into play until you get into much larger sizes than probably most of the residential stuff. But it explains how you size that piping, ways you can reclaim heat from that line, some really interesting mounting options that are in there. So I would suggest that you get both of those and add them to your library if you don't have them. So,
well, Bob, can I interject for the
yep.
very important trivia question?
Okay.
Travis Ball, he is saying The Bug by Mary Chapin Carpenter, 1992.
Right.
How does that sound?
You
Do we
got
have
it
a winner?
all. I've listened to the song forever, like most of us have. I didn't know the name of it was The Bug until I started looking it up today to make sure I had it right, make sure I got the right answer to the trivia. So yeah, thanks for playing. And we'll get we need your size and a mailing address, and we'll get a T-shirt headed your way.
Yep.
So,
Thanks, Bob, and congratulations, Travis.
yeah, so expansion tanks. So this was kind of interesting. I did some research on these too and learned some things over the past week as I was getting ready for this. And I actually found online a picture of a wooden expansion tank in a house in, I don't remember now, it's Vermont or New Hampshire, somewhere back in New England. It was an insulated wooden, just open container. And I guess back in the day, that's what they used for expansion vessels. In fact, we had a fellow, one of our colleagues from over in the UK, came and did a webinar for us years ago, and this was a picture he sent me. They still have these vessels up in the attics of homes in different places over there in his territory. This one obviously is insulated, but you can see it's just a tank up in the attic, and that's how the system is pressurized with this. I don't know if you can see it there, looks like a copper tube going to the outside. So it is an open to the atmosphere type of expansion vessel that's still in use today. So. But we've kind of evolved a little bit from that. Number one, why would you want a tank of hot water up in your attic? Number one, you got the weight, you got the freeze concerns, as you can see here by the insulation jacket, and also, some heat loss going out of that tank through the vent to the atmosphere. So probably the next evolution was a pressurized system, and there's examples of the old riveted style tanks. Some of you guys have probably seen those in older buildings. It was actually a tank that they rolled together and big rivets in the end that put it together. And then, I don't know, those are called sometimes plain steel tanks, I've heard them called, compression tanks, standard expansion tanks. I mean, there's different names for these type of tanks right here that typically they're going to be suspended, above the boiler, right in the floor joist, right above your head when you're looking at the boiler. And so a couple things you need to know about this type of tank is, number one, we call this an air management system. And what I mean by air management is there's going to be an air bubble at a level inside this tank, and it needs to stay in there. That's your expansion space. There's no physical diaphragm or physical separation between the air and the water in that tank. So obviously, if the air got vented out, got lost from that tank, and water filled it up, now you've got a waterlogged tank. And now what can happen, of course, is your pressure relief valve can go off when the boiler heats up for the first time. So we need to be careful on how we set those up, and we need to make sure that we maintain that air bubble in there. So over the years, different companies, I think this is a B&G example here. I think Taco actually made a little mechanism like this as the B&G air troll fitting. And so basically, if you look at it, the way it works is there's actually a tube that goes down through this little connection in the side of the boiler there that's into the water. And then up here is where the air rises out of the top of the boiler. Remember, we talked about that in one of the earlier webinars about that being the best place to get air out of a system is the hottest point in the system and the lowest pressure point in the system. So just happens to be the top of a sectional cast iron boiler is a low pressure zone. It is the hottest point in the system. So it's a great place to grab the air. So what this little fitting does is it grabs the air, and the air goes up through here, and it goes up into the tank, and the air is at the top of it, and the water's at the bottom. And then notice also in the tank, there's an additional fitting up here, and it has like a little standpipe or a little dip tube in it that goes up in there so that water doesn't thermal siphon in that tank. Number one, you could lose your air bubble, but also you don't want to heat up that tank every time the boiler starts up. So it helps prevent that tank from getting warmed up every time it goes up there, because I have that little separation there, and it also prevents it from thermal siphoning. You can still lose the air bubble in these, because what will happen is, and we showed this on, I think, one of the first or second webinars, is you heat up water, air comes out of solution. Well, the opposite also happens in the winter, or in the summertime. If that boiler goes down to an ambient temperature, that air that's in that can also be reabsorbed in the water. And then when it starts up again next time, you can lose a little bit of that air bubble. So over the maybe years it would take to do that, you can actually lose that air bubble out of there, because your fill valve is going to come in and fill up that system and eventually get a waterlogged tank. So, you can still buy them. I know a supplier up in Chicago that still sells these plain steel tanks, pretty pricey, and they work. The other thing that's important on this is this piping that goes up here on this horizontal section. You want to pitch that up. You want to slope it up about 1/4 inch per foot, typically like you would do on a drain pipe or a vent pipe. You want to have a little bit of pitch to that so the air can rise up through that and get into the tank. But both these fittings should be used in conjunction with one another. The fitting that goes down into the boiler, that's got the, you can see the design with the tube inside the tube here. And then of course, that's your system water, goes out of the top of it here. So basically what's happening is the system water should be all water, no air in it, because the air is going to be captured here, going to go around the outside of that and up into the tank. So yeah, they can work pretty well. That tank is going to get warm as it heats up. So there's, a lot of surface area there. You've got a radiator basically. So you've got a bit of heat loss in them. And you'll see when we get to the bladder tank here, they can be about half the physical size of it once we separate the air and water. Excuse me. So now over here on the left is a couple examples of probably the tank that you're more familiar with. This is what we call a diaphragm tank. Again, think of an Amtrol, Watts. A lot of people make these. Zomet, there's some imported tanks out there. And basically this one ring that you see when you look at a tank on the upper part of this, you'll see a crimp ring, and that's where they crimp that little, there's actually a hoop or a band inside there that actually holds that diaphragm in there. So you've separated your water from your air. I don't know that anybody does. I couldn't get a final answer on this. I heard back in the day they used to charge these with nitrogen because it doesn't go through the bladder as quickly as oxygen. I don't know that that's still true. Somebody told me that one of the manufacturers just use chilled air, which they chill it to dry it, so you don't put humidity, because this is just a plain steel vessel here. So by chilling it, you can take some of the humidity out of the air, and then you don't get the potential to have rust inside there. So if somebody knows the exact answer, I couldn't get an answer from one of the manufacturers that I contacted about that nitrogen charge in there, if it's just chilled air is what somebody suggested. Now another style is this style here, and this is sometimes called a bag type of expansion tank or a bladder type of expansion tank. And this actually has a, I don't know, EPDM or butyl rubber, whatever the material is, actually has a bag in it. And you can usually recognize this style tank because it's going to have a flange with some bolts in it. That's how they load it in there. And it can also be replaced. You don't typically see these in small tanks, although you can buy a small residential size number 30, number 60 with this type of a bladder in it. But it's usually the larger tanks, more of a commercial, maybe even an ASME tank that you'll see is this type. Unique about this, it's a full acceptance tank, because you can see in this one here, you can't stretch this diaphragm all the way to the bottom of that tank. That, in fact, the MTRO book tells you about what percentage you want to stretch that diaphragm in there. So you're going to have a bit of the tank that's not usable as far as water going into it, acceptance. Where this type of expansion tank, as you can see in the picture, you could fill that entire balloon or that bladder, whatever you want to call it, with water. So it does have a bit more acceptance volume to it. And of course, a more pricey tank typically, because a little bit more design and engineering involved, that type of tank. So here's an example of an open system. Now, you could have a system, I'll show you an example, one of these here, that's just open to the atmosphere like that and have a little bit of space at the top, and that could be your expansion tank. And you'll see this in some of those outdoor wood furnaces or outdoor wood boilers, whatever you want to call them. They're typically built this way. It's an open to the atmosphere tank at the top, and the expansion is just the space that they leave in the top of that. So that there is the point of no pressure change in this. Whatever the water level in that tank, that becomes your reference point for the circulator and for your system. And again, this is another example of an open system here, because this one's actually vented to the outside. But a couple things I want to caution you about this type of system, and this comes out of I know a lot of numbers on here, but let me go through it slowly. Comes out of Hydronics number 10, I believe, one that we did on wood boilers. So let's start over on the right-hand side. So here's a wood boiler, and this is an open atmospheric system. This isn't pressurized. Some of them are, I know, but this one here is a more common, just open the atmosphere, which is why I think they get away from calling them boilers, because they're open vessels. They're not a pressurized vessel, so they get around probably some ASME listings on this. So what happens with this system, when you fill it up, there's the water level in it. And let's say this is at sea level, just to make the math easy on this. So the pressure right there is going to be what, 14.7 PSI is what it is at sea level, atmospheric pressure. So if you think about this, if I need to get water up to the baseboards at the top of this, let's call this a 2-story or 3-story building, whatever it might be, this circulator pump's going to kick on the first time. It's going to take the water out of here, and it's going to fill it up, and that water is going to be inside this system. And that water will stay up there as long as you don't break the siphon. If you put an air vent up there or a vacuum breaker and you let air in there, every time that pump shuts off, that water is going to drain back down into the boiler. It will stay up there as long as you keep this a sealed system. So what we know about water, it takes just under a half a PSI, it's actually 0.433 pounds of pressure to lift water up a foot. And that could be a column of water, it could be the ocean, doesn't matter. It's just how much it takes to lift water up a foot. So let's say this dimension here from the top of this water level in this boiler, sitting right here, to the top of this baseboard, let's call it, is 15 feet. If I took 0.433 times 15 feet, you can see I've got a negative pressure condition up there. I've got a subatmospheric condition in this portion of the system. And so what can happen, what we know about water when we pull a vacuum on it, is we lower the boiling point of water. In fact, we know that if we go up in elevation, if you go up to the mountains to about, I think it's about 7,500 feet, water boils at 198 degrees because there's less atmospheric pressure on it. Well, that's essentially what we're doing here. We're taking our baseboard a little ways up the mountain and we're lowering the pressure on it. So the other thing that's important is we know that we need a certain amount of pressure on water to keep it from boiling. And so if you look at the graph right here, at sea level, 14.7 pounds atmospheric pressure, water boils at 212 degrees. Anywhere under this line and any temperature that I show on the bottom axis here, I can boil water. I can boil water at 100 degrees. I can boil water at 150 degrees if I pull a subatmospheric condition, pull a vacuum on it. So if we look at what's going on here, and if we take this number right here, and we see that the go out here to 190 degrees, and you'll see that point right there. I don't have an exact thing, is 9.5. So if you take the point 14.7 at 9.5, you can see that we can boil at this temperature here. So obviously negative 6.5 is lower than negative 5.2, excuse me, so that I'm going to boil water at 190 degrees in this section of the building. And what that's going to sound like is somebody's got a hammer and they're just banging on your pipe up there because you're flashing the steam. You've probably heard this in a boiler, like a ModCon boiler, when the pump stops running and you hear that banging and clattering, you're flashing the steam in there. That's what happens inside this. And there's really nothing you can do about that unless you could put maybe a plate heat exchanger in here and pressurize the building, keep the open system on one side of the heat exchanger, pressurize your building, and you don't have that condition. And what's interesting about this vapor pressure and how we can get down to boiling water at these lower temperatures, some of you folks might be familiar with or have seen these on the roof. These are evacuated tube type of solar collectors. And this is actually when I make a little coffee cup, I just put this out in the sun here and I can actually boil water. I got a copper cup that slips right on that heat pipe. So the way this is built is they put a copper tube in here and they put a fluid in there. And I believe it's a water methanol mix. So it's got a little bit of antifreeze protection to it, not very thick. And then they seal that and they pull a vacuum on it as they seal it. And this tube right here, I went right to the manufacturer's website, will vaporize, will boil at 86 degrees. So way down here, and they do that by pulling this sub-atmospheric, pulling a vacuum on that tube before they seal it. So now I can put, in fact, this was a winter day, you don't see snow there, but it was in fact a winter day. It was like 35 degrees outside, and I just set this out in the yard. You can see a blue sky day here. It was a sunny day. And I set this out in the yard at 30-some degrees, and I actually boiled water in that copper cup in there and made a cup of tea of it. So there's an example how, if we use that vacuum on a fluid, we can lower that that boiling point. And so you can see right here, this example that we're boiling in there at 86 degrees after 30 degrees C approximately.
Hey Bob, this is Kevin.
Because the folks in New Zealand asked for that. Yeah, Kevin.
Daniel's wanting clarification. Can you tell us where you got that negative 6.5 again, real quick?
Let me go back here. It's a 0.433, which is what a PSI to lift water per foot times 15 feet. And it's going to give you a negative number when you do 0.433 times 15 feet of elevation. So whatever elevation you want to call that, times the PSI that it takes to lift water up a foot, that's where that negative 6.5 comes in. And in this number here, this 9.5, that's just where water, we're assuming that this thing's running at 190 degrees. So if you go up here at 190 degrees and you run up, that's going to be about negative 9.5 PSI.
Okay, thanks. Hey, while I've got you, Travis wants to know, why do all wood boilers seem to be open systems?
Well, I think it's to get around some of the pressure vessel codes myself. I don't know that because really they're called outdoor wood furnaces, not boilers. I think once you start calling something a boiler and it's a sealed pressurized vessel, I don't know that for sure because I used to sell Aquatherm outdoor boilers and those were actually pressurized. So I don't know, maybe it's the thickness of the metal that they have to use to make it a pressurized vessel. I'm sure that has something to do with it. I know some of those are just basically a tin can, to be honest with you. Some of those less expensive outdoor wood boilers, there's not much metal to them. So I would imagine it has to do with pressurizing the vessel that's made out of a thin gauge steel. If somebody knows that, I don't know if the Aquatherms that were made up in Minnesota, I don't think those were ASME listed, but it's been a long time since I put those in.
Okay, yeah, thanks. And then Wheels said, it's all about money for open atmosphere wood boilers.
Yeah, I'm sure it is. It's a pretty price point product. It's, what's the least expensive way I can heat a house? Number one, burn the wood, burn your furniture, whatever you have to burn. And it's really, to me, it's just a barrel suspended over a campfire. I mean, I'm hoping I'm not stepping my manufacturer's toes out there, but there's not a lot of technology to those. But, people, I see them all over. People have been using them for years, and they certainly turn wood into heat. So, at least there's a hydronics application for us in that. The problem I have going back, since we're on this topic, is this thing will go through circulator pumps like crazy because you don't have any suction head pressure on this. In fact, I see Taco just came out with a new pump. What do they call it? A 0034. I just got a little thing on it. And they actually put the net pump suction head required at 200, I think they rate it at 203 degrees, or I don't know, it was a high number. I don't know why they chose that number, but you need to have a certain amount of positive pressure on the circulator pump, especially when you run at that high temperature, or you're going to cavitate that pump. And I know people replace these pumps every year or two because they just cavitate them to death. In fact, I think Taco makes a specific pump for that. It's an open frame motor instead of a wet rotor motor, which maybe lasts a little bit longer than that severe application. But yeah, it's not a great application for a circulator pump.
Well, Bob, if I can interject, I also have some important information about the song "The Bug" that
Oh, okay.
Steve Dodds has said. Now, he said that this song is actually written by Mark Knopfler and was
Oh, really?
originally performed by the Dire Straits Band on the final
Oh.
studio album.
Hmm.
And it was covered by Mary Chapin in 1992 and was recorded on and my goodness, he's got so much information, but long story short, what do you think? Is it a two t-shirt night?
Yeah, I would say that's a bonus answer. And I did learn that she won 5 Grammys. In fact, she's the only female artist to win 4 in a row, which is, I guess, an accomplishment that nobody's been able to touch since then. So, yeah, that surprised me. That was written by Mark Knopfler, but it's a good tune regardless. So, thanks for that information. So
Yeah.
now I got another trivia question
Yeah.
for another.
Thank you, Steve and Bob. Thank you. Appreciate it.
Yeah. So when it comes to size and expansion tank, there's all sorts of sizers online. Pretty much anybody that makes an expansion tank, I just grabbed this example from Wessels, which is West Tank is their website there at the bottom. What I would say is when you go to use one of these sizers, I know Amtro, I'm not sure about Wessel, they'll have like a residential and a commercial sizer. And the residential one pretty much asks you the BTU of the boiler, not a lot of input information. If you really want to get, the exact number, or you want to get a selection of different model numbers that might work for that. If you go to their commercial sizers, you're going to get a window that opens up like this one. That's going to ask you for more information, volume of the system, the temperature that it starts at, the temperature it's going to run up to, your static fill pressure, and what pressure that you can accept that it goes up to. Obviously, that's going to have to be under your pressure relief valve sitting. So you can get a little bit more a better answer, especially on a bigger job, if you want to make sure that you're not oversizing a tank by using these the commercial sizers. And actually on the Wessel website, they have a conversion if you're going to take out an old compression tank or plain steel tank or whatever you want to call those, that type of vessel. Here's a typical example. 15 gallons is one of the sizes that's pretty common out there. So you put that in there and it's going to ask you the pre-charge. And then here's the answer that you get when you hit calculate. It's going to show you. And here's an example. So I'm going to replace a 15-gallon tank with an 8.3-gallon tank by going to either a bladder tank, as you see here, or a diaphragm type of tank. And these are just some of the options that they give you both in ASME and non-ASME. So that's, 2 things. It shows you that you can go quite a bit smaller by using a tank that has the physical separation between the water and the air in there. And also, they give you different choices of styles of tanks. Sometimes it might be a base mounted tank or like you see a bladder or diaphragm type of tank. But my favorite of all the expansion tank sizers, and I know we plugged this for Siggy a couple of episodes ago, is this is, you can see right over here about the 4th toolbar in there is an expansion tank sizer. And what I like about this one, it lets you put a lot of information in there, okay? If maybe you've got a boiler that's got a 45 PSI pressure relief valve on it, so you've got a little bit more wiggle room there. It'll actually show you the distance from the top. That's where the point is, from the top of the expansion tank connection into the system to the highest point in the system. And I like that you can put the pressure at the highest point in the system, because we'd like to have a positive 5 pounds of pressure, PSI, at the highest point in my system. If it's upstairs, if it's on the indirect tank sitting right next to the boiler, whatever it is, the highest point in the system, I'd like to have a positive 5 PSI. And I want that in there, so if I've got an air vent on there, in addition to the float and the air vent, I've got a little bit of positive pressure that's helping me make sure that that air vent gets a nice tight seal on the top of it. So the height of the building, add 5 pounds pressure there, and put in the rest of the information. So if you can see some of the piping, or you know what the piping is when you built the system, you can put all that information in there, and that gives you the fluid volume of all the piping. So that helps a little bit, get your number a little bit tighter. Miscellaneous for your boiler, maybe you've got an indirect tank or something that holds a little bit of fluid NITS coil. You could put that in there under miscellaneous. Again, your temperature extremes, the hottest temperature is going to go to, the lowest temperature, and there you go. You get all the information that you need for pressurizing the tank and the system volume and all that information. So it just gives you a little bit more to play with. So if you want to play what if scenarios. We did, by the way, if you want to go back to some of the past Caleffi webinars, Jody Samuels worked for us for a while, and he used to work for Amtrol, and he did a really good job on explaining expansion tanks with the longhand sizing. There's actually tables that you can use, and you can cross over. It took him about 4 pages to get through all the tables, the pressure and the temperature relationship to size an expansion tank exactly. But again, you can see with these little simulators, why wouldn't you just plug in some numbers and click calculate and get an answer? But if you want to know, and by the way, all that information is also in this engineering guidebook from Amtrol. It's got all the math behind how you build these calculators, basically. All right, so this has been controversial all my life, going on, what, 40 years now, whatever it's been that I've been putting systems together, is the proper mounting position for an expansion tank. And I've always been told, you know, from the nipple, hang it down. But in fact, here's right from the Zillman installation manual I found today as I was researching a little bit on expansion tanks. They actually show the standard position with the nipple down and the tank facing up. In fact, the label's even upside down in that example there. And they show this as an optional, which is, I thought was counterproductive, or you know, counter what I had learned, that you always want to hang them down. And actually in the Amtrol book, it actually says this is the preferred, but they can be mounted horizontally as long as you support them properly. So it says at the designer's discretion, they can be mounted horizontally. I don't know that it shortens the life that much by having it in there, because you can trap some moisture inside that steel tank when you put it upside down like this. But I've seen tanks that have been laying on their side for 20 some years and they're still working fine. So I don't know that I have a final answer after all that, to make that long story long. And here also on the Zillman site, they show the domestic water tanks in all 3 different positions, upright, hanging down, or off horizontally. So I don't know what to tell you about the best way to put them in, but I think forever they've been mounted this way because there's always been a provision at the bottom of the air purger to do that. Why wouldn't you use it? It's a nice solid mount for the most part, because it's been piped with copper, steel pipe, or something like that. So you don't have to put another support on the expansion tank. So, but what's changed about that, especially with the new ModCon boilers that they want you pumping into the boiler, we don't necessarily have our expansion tank up on the air purger anymore. So now we've got to get some kind of mounting arm or mounting bracket or another way to support our expansion tank. So with that in mind, maybe you would lay it on its side up here. I've seen people, I saw a job out in Colorado once, John Myrtle, some of you guys might know him. It was a fire station. He didn't have much room for the boiler, much less all the other parts that went with it. And he actually built a unistrut rack, and he had 4 number 30 tanks. He just had a little bit of space, and he had 4 number 30 tanks manifold together on a unistrut rack, all mounted horizontal. And I'll bet those are still going. That was 25 years ago or something that I visited him at that job site. I'll bet those tanks are probably still up there working fine. Of course, you got to adjust the pressure in all of them, make sure they're all set at the same pressure, and you want to keep them mounted in the same place. Don't put one up at the ceiling and one down at the floor, because now you're going to change the acceptance volume of the one that's you know, mounted in the different elevations, so to speak. What else do I have there? Really, what I think is the makes an expansion tank go out sooner than later is if you've got one connected to an old non-barrier tubing system. I've walked in mechanical rooms where I've seen like 3 rusted out expansion tanks laying on the floor next to the boiler, and the owner says, yeah, every 2 or 3 years we got to replace that tank. Well, it's probably not the tank if they're going down that quickly. And most of the time I've found that's an old polybutylene system, or maybe an old rubber tube system that didn't have a barrier tubing on it, and oxygen's getting in there. Oxygen's migrating through the wall of that tubing. And where's the weakest link in any hydronic system? It's the sheet metal thin expansion tank is typically the first thing that's going to develop a, you know, one of those paint blisters or a little pinhole eventually when the tank fails. All right, so how am we looking for time here? Yeah, we got time. The point of no pressure change. So the point of no pressure change is what you establish when you put the expansion tank into a piping circuit, and you get to choose where that is. And it can be in different places on a system. And every system you look at from this day forward, when you walk into that mechanic room for the first time, I want you to notice where the expansion tank is, number one, in the room physically, but also where it's connected into the piping. because what we want to do is we want to establish a point so that when the circulator starts, it adds all its head, the mechanical energy that that circulator imparts to the water when it starts spinning, turn electrical energy into centrifugal motion into mechanical energy called head. We want that to show up as a positive everywhere in our piping system. So let's just take an example. So what we know about water, what we should believe, is that we can't squeeze water and compress it, not under these type of pressures. At extreme pressures you can a little bit, but you can't compress water and you can't stretch it. So if this was a closed loop piping system that I filled up to 10 pounds static fill pressure, these gauges are all at the same level, I can't take water out of the system and I can't add water into it. So this connection point right here, if this is pre-charged at 10 pounds of pressure before you put it on there, fill it up, get all the air out of it, 10 pounds of pressure, there's nothing that this circulator pump can do in itself to change this point right here, this pressure at this point here, because it can't suck water out. Where would I put it? Can't put water in. Where would it come from? So that's the point of no pressure change. So now what's going to happen? Now what can change the pressure there? If I put a boiler in here, if I put fire on this pipe and I heated that water, it's going to expand. And yeah, that pressure at that point of no pressure change can in fact go up, but not by the circulator by itself running, doesn't change that point of no pressure change. So let's throw a little pump in there, a little circulator. I don't know, it's green, let's call it a 007. And as that circulator starts, if I hit a gauge right on the discharge side of that, remember, I've got this filled up to 10 pounds pressure, it's gonna be 10 pounds. Here's a little thing for you. So I've got 10 pounds on every one of these gauges. They're all at the same level. I just went around the room at a foot off the bottom of the floor maybe and put a loop of fin tube, whatever, on that. Suppose I came here and there was a doorway here and I had to go up and over the top of that doorway and back down, and let's say that's 7 feet that I had to go up. What would a gauge up here 7 feet above this read? Because remember, I went up in elevation. Well, you take that 0.433 that we talked about earlier times 7 feet would be, I don't know, was that 3 PSI approximately lower pressure up here, 7 feet up, where I had to go up and over the top of the door. So keep it simple. We're at one level. So now the circulator starts, and you can see that it's going to add, in this case right here, about 8 pounds to the static fill pressure of 10 at the discharge. Now, as I start going around the pipe and I go around an elbow and I go through maybe some fin tube, whatever might be in here, I'm using up that head energy that the pump has imparted to that fluid gets consumed or used up as I go through a pipe, as I go through an elbow, I go through more pipe. You can see I'm down to 15 pounds, I'm down to 13 pounds, come around the last bend here, I'm down to 11 pounds. I'm still at 10 pounds of pressure here. That doesn't change. Now, notice I show a little bit of droop between there and there. Unless that expansion tank was connected exactly right there, there's always some pressure drop. Even 2 inches of pipe has pressure drop at a certain flow rate. So again, this is just a, an example. You'd have to put numbers to what this pipe is. You'd have to put numbers to the size of that to know what these numbers would change to exactly. You'd have to calculate the, the pressure drop through that circuit. So this is good for a number of reasons. Number one, we always want positive pressure in our system. We don't want to pull down to that subatmospheric condition because of what I just showed you. We could boil water in there. But also, a lot of the new boilers, some of the new boilers, I should say, have pressure switches on them. And so they want you to pump into that boiler to get this additional delta P that we're adding, shows up in like the Geonomy type of heat exchangers, and some of them have a little diaphragm type pressure switch. And if that pressure drops below, I don't know, maybe it's 8 pounds, I don't know exactly what those pressure switches are for, that boiler's not going to fire and you're going to have a callback. The boiler's not firing up, there's no heat. Maybe you burped a little bit of air out of here, your pressure dropped down, and now you don't have now you've got a no heat call. So this is good. This is what we want. We want that circulator pumping away from the point of no pressure change. Now, I might have a job where I've got multiple circulators. I might have a complicated primary, secondary with a dozen circulators all mounted in different places in that mechanical room. Where's the point of no pressure change for 6 different pumps? Well, I'm going to talk about that as we get a little bit deeper into it here. Looking good for time. Any questions, Mary or Kevin or anybody that's hanging in there?
No, so far so good, Bob. Keep going.
All right, thanks. So you can see what we did on both these drawings, the previous one and this one. This is just Siggy took them and kind of made them, I think, a little bit easier to follow. This is the original Bell and Gossett drawing from, I don't know, 1960 something, I would guess. By putting in color here and putting some, color and some numbers and some gauges to it, a little bit easier to follow. It's the same drawing. It just clears it up a little bit for people putting in Technicolor. So let's take that same example and let's change a couple things on this drawing. And number one, I'm going to move the expansion tank from the suction side of the circulator to the discharge side of the circulator. I'm pumping at the point of no pressure change instead of pumping away from it. The other thing I did in here, just to make an example of this, I lowered my static fill pressure to 5 psi. Now remember what happened the last time. The circulator pump started up and it added its positive pressure to the discharge side of the circulator, which showed up as a positive all around the system. So now the circulator starts and said, hey, you know what? Something odd's going on here. I can't change the point of no pressure change above 10 psi right there. I can't push water into that. Where's it going to come from? I'm going to make my pressure differential from the suction side of my circulator. So now I took that 8 pounds of delta P that pump could add, and I subtracted it from my 5, and look what happened. I've got a negative pressure condition. In fact, probably starting about halfway around this loop right there, I've pulled down to 0 psi. I've got subatmospheric conditions all the way down here, all the way around to that. So guess what happens, which I'm going to show you here in a couple minutes. What would happen if I had an air vent anywhere from here to here to here to here, all the way back to here, and this circulator starts up? You're going to see air coming into an air vent and filling up my system here in a couple minutes when I put it under this condition. Because again, I've just pulled it down below my fill pressure down below a subatmospheric condition, and now I've got a negative pressure condition in there. You know what? This would probably circulate. Water would probably go around this just fine. In fact, I'm going to show you this one here. I'll pull down below that, and water keeps circulating around it. Again, the problem would be any air vent in that system. If you had a leak around a packing on a ball valve out here somewhere, you might get a little bit of air pulled in around that, and that's going to present itself by an air problem that never goes away. You go back and you purge it out, and Mrs. Fernwicky calls you a month later and says, I've got air in my system again. You got to come back. You know, what's going on? How come I keep getting air in my system? Every time somebody purges it out, it comes back, it comes back. This is what I want you to look for. I want you to look and see where that expansion tank was connected into that system. So what do I do here? One of two things. I either move the pump here, or sometimes it's easier just to cut and cap that off, and I could leave it right there physically and just take a piece of copper tube or PEX tubing and just mount it over on the intake side, the suction side of that circulator. And immediately upon doing that, I would get back to this condition right here, where all my head that I'm developing by the circulator shows up positive all the way around the system. Simple enough. You know, it took me a few times to understand exactly that concept, but again, read through pumping away a few times and you should have that down, that you can repeat it and explain it to somebody that doesn't understand the difference between expansion tank connection points into a system.
Hey, Bob, so just to confirm, you can have more than one expansion tank, right? They just need to be at the same level?
They need to be at the same level, and they need to be pre-charged to the same pressure. Now, an interesting thing, I was talking to Dan the other day about this a little bit, and he's, like I say, he's going to do a presentation on this. He said one thing that would happen is, he said, you don't want to have two expansion tanks in the system at different locations, because then you've got an unknown point of no pressure change. Somewhere, let's say somebody put an expansion tank here and here. Well, now where's the point of no pressure change for that pump to reference? And he said where they had problem with that years ago is you would fill up an old system that had cast iron radiators, and if somebody didn't open the vents on those cast iron radiators and get the air out of that, now you had an expansion tank in the top half of your radiator, and you've got multiple points of no pressure change in your system, because those radiators are acting like expansion tanks, like a compression type of expansion tank, because they've got an air bubble trapped in them, and now you've got an unknown point of no pressure change in that system.
Another question for you, Bob. Where's the best placement for the expansion tank on a ModCon boiler that's piped primary, secondary?
Yeah, and so here we are. I'm going to show you that exactly. And in fact, I'm going to show you a problem with this system here. So this, if you look at this, you say, well, that looks like a great place for an expansion tank. This pump that's pumping into the boiler is pumping away from it. Now, in this example, one or the other is going to run here. They don't both run simultaneously. So on a call for domestic hot water, the main circulator shuts off here that's going into the loop over here. This we'll call the primary loop, because the loop that has the expansion tank connected to it, I learned this recently, is the primary loop. So if I would have connected this tank in over here, this would be the primary loop, the boiler loop. This is the primary loop. If it was over here, that would be the primary loop. That's what I've been told. I know there's different opinions on that, even from the people that, excuse me, the boiler people out there, as far as what's the primary loop and what's the secondary loop. Excuse me, but that's how I understand it, the loop that has the expansion tank. So one way you could figure out what's going on in the system is make a graph of it. Now you could put numbers to this if I knew what this piping was, what size, what the elbows were, if I counted up all this and, excuse me, determine my developed length of all that tubing, I could put numbers on this. But if you look at what's going on here, when I've got the domestic hot water is calling, and this pump is running, this pump is off, you can see what happens to this pressure profile going through there. I'm starting down here below my static fill pressure. The pump kicks on. I'm showing a little bit of increase there. I'm going through some piping. I'm going through my heat exchanger pressure drop here, which could be substantial in this case because that's a Genome heat exchanger, for example, which is the one, excuse me, that I have an example behind me. A little bit of pressure drop going through the piping here. Maybe a lot of pressure drop going through an indirect tank that has a small diameter coil. So you can see these 2 points are the same. Excuse me, sorry, that happened last time. But what I don't, excuse me. Get a drink, give me a minute. Hope my voice comes back. I don't want to drop down below my point of no pressure change because now I can I could flash the steam in here. Oh, this is crazy. I'm losing my voice. Did I get too many words out already tonight? So I don't want this condition to happen. So let me show you what we could do in this. We could just move this expansion tank to a better spot because I don't want to fall down below my static fill pressure. So what I did here is I just moved the expansion tank over here. So now if you look at this, you say, well, that's great. This pump is pumping away from the point of no pressure change because you moved it over here. But what happens when I've got a heating call? Isn't this pump pumping right at the point of no pressure change? Well, a couple things are going on here. Is number one, there's a check valve right here. So when this circulator's off, oh, thanks. Got some Tic Tacs from my production assistant here. When this circulator is off, there's a check valve is shut there. So now this pump can't see this point right here, so it's not going to pump at it. So what is the point of reference for this circulator here? Well, it's going to go, this expansion tank is going to go through here to B, through here, through the closely spaced T's, and this pump is actually pumping away from the point of no pressure change. And I know that by looking at the graph over here. See what's changed on the graph is from the minute the pump starts, the circulator pump now on the heating circuit, I show that positive pressure, and then I have, again, I drop a little bit through my piping, drop a little bit through my heat exchanger, drop a little bit through my piping and drop a little bit there, but I don't fall below my point of no pressure change in either condition here. Obviously, when this one's pumping away, but this heating injection circuit, let's call it, in the loop over here, when that's running, it's referenced the point of no pressure change through this piping right here. So there's an example. So I would like to, you know, if it was a different scenario where I didn't, maybe I had my indirect tank over here on a zone pump or something like that, and I didn't have the circulator here, then this would be a great spot because now I'm pumping away from the expansion tank. I'm pumping into my boiler. I'm adding that delta P into my heat exchanger. I'm showing a pressure increase in that boiler every time my circulator starts. Everything's fine. What threw a wrench in the works in this drawing right here is having the two different circulators and having checks on them that close off that point of no pressure change reference to both those circulators. So you got to be careful with that. You know, when we started putting check valves in the systems, you got to think about, okay, now what direction does my point of no pressure change get to that circulator pump? And so the same thing here. These circulators are pumping away from the point of no pressure change. Over here is call these my zone circulators going out to my distribution. They see this point right here as a reference for pumping away. This is pumping away, and through this reference point right here, there it is. Any questions or anything, Kevin? I got a couple more slides, and I think we better get to the demo here.
Oh, here's a comment. I think Wheels said, be careful on ModCon boilers. Some have circulators and diverter valves built in. And the manufacturer of the boiler, something about the placement of the expansion tank, you could blow off relief valves.
Yeah, I mean, if you had too much, certainly if you had too much pressure above the relief valve setting, you could do that. And I've seen that happen with high head circulators too. They have a static fill pressure of maybe 15, 18 pounds. They put a high head circulator on it. Now, yeah, you're going over the 30 PSI. So I know some of those boilers that have pumps in them also have expansion tanks in them. I've seen where they come with their own expansion tank in the boiler and their own circulator pumping that. So, you know, read the directions, I guess, is probably the best thing when you're working with an unfamiliar a boiler system like that, so you know that you've got it in the right, where everything's going to be on the same page and work together. Well, thanks for that, that reminder, Wheels. Thanks for showing up today too. I hope you're well. So I just put a handful, and I'm sure people could add to this list of probably some of the most common best practices, because again, you know, I don't know that there's one way that you're going to get everybody to agree on the proper way to mount an expansion tank, but just know that if you're going to mount it somewhere other than on a, you know, an air purger that's suspended, you know, with the piping and has enough mounting to carry the weight of that. When a tank gets waterlogged, they get pretty heavy. So let's say that holds 5 gallons of water times 8.34, whatever a pound of water weighs. You've got quite a bit of weight there. So I've seen people take those low expansion tank brackets and just screw them in the sheetrock, thinking that's going to hold the weight of the tank. And trust me, when that tank gets waterlogged, it's not going to hold the weight of it. So on the second point here, always check the pre-charge before you connect that tank into the system. And I would get an accurate gauge, like an RV gauge, that maybe only goes up to 30 pounds pressure. So you can see if you go out in your truck and get 100 PSI air pressure gauge, you're probably not going to be able to get a very accurate setting on that expansion tank. So invest in a good, accurate pressure gauge that's, you know, in the range that you're working in. Isolation or check valves. I know a lot of the manufacturers, valve manufacturers now make expansion tank specific isolation valves that even have a drain port. So someday if you do have to take off a waterlogged tank, shut the valve off, put a hose on it, drain the pressure off, and then you can take it off without having to, you know, pound a sack of concrete in your arms all of a sudden when the thread comes off on that last turn. I did see in the Amtro book, they said to use a lock shield ball valve if you're going to put a ball valve or something on there that you can lock it so somebody doesn't turn that handle off. Some people just take the handle off and, you know, hang it on a wire somewhere in the room or just take it with them. There's also check valves. We sell check valves that you can put on expansion tanks. And I should have had one here. What happens with that check valve is when you screw the tank into it, it pushes open the check valve. So if you unscrew the tank, the check closes and you can take the tank off without losing any fluid. One of the issues with that is a lot of people don't realize that's what that valve is, that's a check valve in there, and they go and unscrew the check valve in the tank and everything at once, and now you're back to where you were before you put a valve in there. So we talked about this, you know, if you put the tank below the static pressure, you know, like I said, if you put one tank up here and one down below it, a little bit of change in pressure there, keep them at the same level. We talked about that. It does talk about, and if you're running high temperature systems, to put a little piping distance between the where you connect into the system and the expansion tank, just so you cool that water a little bit. Not a huge deal. Most of them are rated for that temperature, but they say it will extend the life of that bladder if you don't have it running at 220 degrees, for example. If you're going to use a tank on an old non-barrier tubing system, polybutylene, whatever it might be, I would definitely get I think Amtro makes a -R tank, and I think it's epoxy coated or it's got some sort of coating in it, so it can handle the oxygen that's getting in the system. Solar expansion tanks, you know, use the solar expansion tank sizing information for that, because you'll see a large delta T. You know, you could have my solar system in the wintertime could be 0 degrees outside, and it could be, you know, 200 degrees on another day. So you've got a huge delta T there that tank has to see in that type of system. And also I learned this, I took I don't know, one of the German solar trainings years ago, and they talked about a safety seal, which I had never heard before. And they said what they do, or they suggest on glycol solar systems, they said size your tank, you know, generously sized so it's big enough for that wide delta T. And then they said fill your system and put a little bit more pressure in the tank when you fill the system than you did on the air charge. And they said that'll put a little bit of water, maybe a gallon or whatever it might be, depending on the size of your tank, in there. And they said that's in there. So if you fill your system at, say, 50 degrees in the basement of somebody's house, winter comes around, it drops to 0 degrees, somebody's going to go down and say, well, I've got zero pressure in my solar system, I got a leak, I got to call my guy, come back, the fluid must have leaked out of the system. Well, in fact, what happened is when the temperature dropped that much, you know, the pressure went down. So they say that little bit of safety seal in there keeps the gauge from going down to 0. So makes sense, but obviously you want to make sure the tank is sized sufficiently if you're going to do that, because you've used up some of the expansion space. All right, so I'm getting a little carried away here. So here's the demo. It's a 3-minute video today. It's just one video. So what I'm going to do, here's the little demo I built. There's a little Geonomy heat exchanger. I've got a couple circulator pumps here. I've got some gauges in here. I'm going to show a couple different things. I'm going to show what happens when I pump. See, with these valves here, I can change where my expansion tank, this is a flat type of expansion tank, a little manifold here. I can pump away from the expansion tank with both my pumps, pump away from the expansion tank with one of the pumps, and I can pump at my expansion tank with both these pumps running. So these gauges are going to show my static fill pressure, 8 psi. And then what the important one is I'm going to show you is when I start this pump, I want you to watch this gauge up here, and I'm going to change the position of these valves, and you'll see when these two valves are off and I open this valve and this valve and I'm pumping at the expansion tank, this is a compound gauge, I'm actually going to pull this gauge down to below 0, and you're going to see this air vent go down, and you're going to see air bubbles. I hope you can see it. We tried to get close enough with the camera that you can actually see air being pulled in here. And then I turn this back off, turn that off, pump away from it here, and you'll see air coming out of this air purger. In fact, there's an air vent up on the top here. You can't quite see it in this picture. I can actually put my finger over that air vent when I'm pumping at the expansion tank here, and I can actually feel that vacuum on my finger. So I got to figure out now how to close this and get back to my my video, and I'll run that video and we'll come back for some Q&A, and we'll be good. So I'm going to end this show and go back to my see, this is what I was trying to make a little bit smoother, but we got it. Howdy. So here's our shop talk demo for this week. We're going to be talking about the expansion tank, the relationship to the expansion tank and the circulator pumps, the gauges, pumping away from the point of no gauges. If you zoom in here, going to obviously read 8 psi, pretty accurate to one another here. And then step back a little bit and I'll show you the whole big picture here. Expansion tank has been pre-charged at 8 psi before I connect it to the system. So I'm just going around. I've got 2 circulator pumps so I can vary the flow that's going through it. I've got a flow meter. I go down. I go through a little Geonomy type of heat exchanger down there in the lower left-hand side. That's just 150,000 BTU heat exchanger from a boiler that I put in there. High pressure drop boiler. That's going to be important when I show you the relationship. So we're going to go here and we're going to start switching things on, and we're going to pay attention to what happens to the gauge as I move the connection point through here from the different pump locations. First, I'm going to start pumping away. Both pumps are pumping away from the expansion tank through this tube right here. Then I'm going to go down to this one where I'm pumping at the expansion tank with one circulator, and you'll see the relationship on the gauges. I'll shut that one off, and the last thing I'll do is go down and I'll turn this one on, and you'll see what happens to the gauge when we're pumping at the expansion tank with both the circulators, moving a lot of flow towards it, a lot of head we're moving in that instance here. I'm also going to demonstrate how the pumps add their delta P, their pressure to the system on this gauge right here. So that'll be the first gauge you want to watch as I start switching things on here. So come on in, take a look. So I'll switch on the first pump first, the top pump I mean first. And you can see we went from 8 pounds to what do we got there, about 13, 14, kind of upside down here, so I can't quite see it. I'd say we're about 13 pounds. So that's how much delta P the first pump is added. Now let me switch on the second circulator and watch the gauge. It jumps up, not quite twice as much, but almost. So that's how much head that we're adding it to with the 2 circulators. And I'm doing that because I've got a high pressure drop boiler going through there. So now up here, you can see we're pumping away from the expansion tank. I'm going to shut that one off, and I'm going to open up this one here. And look what happened to the gauge up here. It went from 8 pounds down to about, I guess 3.5, maybe 4 pounds pressure there, because now I'm starting to pump at the point of no pressure change. Pumping at the expansion tank away from it. Now the next thing I'm going to do is I'm going to open up the bottom one where both pumps are pumping at the point of no pressure change. Pay attention to this gauge up here and watch what happens. When I open this one down here up, I've actually pulled a negative condition. Look what's happening to my air vent. My float sucked down. I hope you can hear it there, but I'm actually sucking air in my air vent right now. I'm starting to airlock my system because I pulled into a subatmospheric or negative condition here. So let me shut that off and just show you what happens in a second here. keep watching the air purger, all that air I just sucked in there now has to come out. And the same thing up here, I was sucking in this air vent. If I open this up when I'm pumping at that point of no pressure change, again, pull down to that subatmospheric condition, and I'm actually sucking air. If I put my finger over the end of this, I'm sucking air in there. And now you can see how my air is starting to show up in my air purger there. So ideally, if you could keep up with the air that you're sucking in your vents here, that vent would do its job. But we don't want that condition. We don't want to pull down to a subatmospheric condition. I'm going to be back in this condition. So that exactly what happens when you start pumping at the expansion tank, especially with high head circulators. You pull your system in a subatmospheric condition, and now my air vents anywhere in that suction side of the pump are sucking air in. That's why you've got an air problem. So I hope that makes sense. Call me. I'd love to talk to you. Thanks for joining us.